Welcome back, everybody, to our second session of the afternoon. And it's a pleasure to have David Poland from Yale talking on fermions and the conformal bootstrap. Thank you, David.
Thank you very much. So it's a great pleasure to be here at this interesting workshop. Thank you very much to the organizers for inviting me and bringing all these people from different communities together. It's really a great opportunity to learn from each other. So I think I may be the only representative from the modern conformal bootstrap community here. So I thought I'll do my best to try to explain to you a little bit about what the conformal bootstrap is, show you some highlights from recent results in the conformal bootstrap in 3 or 2+1 dimensional systems, and then I'll show you some recent results related to conformal field theories involving fermions in 2+1 dimensions. Okay, so just a brief summary of what the conformal bootstrap is. The idea is very simple. The idea is really just to make maximal use of symmetry, in order to try to learn something about conformal field theories. And the idea is that you use conformal symmetry, a constraint called crossing symmetry, which encodes associativity of the underlying operator algebra, along with unitarity, in order to try to map out the space of conformal field theories, solve conformal field theories that are particularly interesting. And in this way, we can learn something about critical points, which are described by conformal field theories. So in practice, the way the conformal bootstrap proceeds is to think about 4-point correlation functions in conformal field theories. So if I have a single operator sigma, I can think about the 4-point function sigma of x1, sigma of x2, sigma of x3, sigma of x4. This 4-point function can be expanded using the operator product expansion. So you say, if I take 2 sigmas near each other, this can be expanded in a sum over conformal primary operators O, in particular local operators O. And there are some coefficients showing up in this expansion, which I'm calling lambda ijk. And we can apply this OPE to pairs of fields in the 4-point function. And in particular, there are different ways to apply it. So we can expand the 4-point function using the 1, 2, and 3, 4 OPEs, or we can expand the 4-point function in the 1, 4, and 2, 3 OPEs. This gives, requiring that these two expansions are equal to each other, gives you a constraint called crossing symmetry. And we can write this as a very concrete equation, because the contribution of each operator O in the OPE can be captured by a certain kind of special function called a conformal block, G of delta and L. These conformal blocks depend on the 2 conformal cross ratios that you can build out of 4 points. The 2 combinations of the 4 points that are invariant under any conformal transformations. And this crossing equation tells you that an expansion in conformal blocks in one channel has to equal an expansion in conformal blocks in a crossed channel. So this gives you a kind of sum rule. It tells you that a sum over a certain special function labeled by scaling dimension and spin of the exchanged operators with positive coefficients has to equal 0. Okay, and yeah, let me just highlight that in this bootstrap equation, these conformal blocks are basically known functions. We understand how to calculate them to arbitrary precision fairly efficiently. And the only unknowns in this equation are the set of scaling dimensions and OPE coefficients of all the primary operators showing up in the OPE. So it's a sort of a nice way to try to learn something about the spectrum of conformal field theory. Okay, so then the question is, how do you extract some information from this equation? And you can try to tackle it analytically in different limits. You can try to tackle it numerically by putting it on a computer. I'm going to focus on the numerical approach in this talk. And the idea is that we basically have some functions that we want to sum up with positive coefficients to get 0. We can think of these as being like vectors in some vector space. And so if you ask, when can you sum up a bunch of vectors with positive coefficients to get 0, you can do it if you're in a situation like the left, where all the vectors sort of point in random directions and you can balance them against each other. But you can't do it if you're in a situation like the right, where all the vectors point to one side of some kind of plane, separating plane alpha. And then in this right-hand picture, you can't sum these vectors with positive coefficients to get the 0 vector. So the basic idea behind the numerical approach to the bootstrap is to ask a computer, can you find a separating plane that puts all these vectors or functions to one side of it? And in practice, the way we do that is by applying a functional to the crossing equation. We look for linear combinations of derivatives with respect to the cross ratios up to some order capital lambda. And we make an assumption about the spectrum. We look for a functional that, when applied to the crossing equation, implies a contradiction, like 0 equals a sum over positive quantities. So if you can find such a functional, then you rule out whatever assumption you made about the spectrum. That's the basic idea in a nutshell. Over the last decade or so, we've sort of been refining this numerical approach. We've been building various software tools to search for these functionals. The modern approach is to look for them by solving a kind of convex optimization problem called a semi-definite program. And there's a nice piece of software called SDPB, which is optimized for solving the kinds of semi-definite programs that show up in the Bootstrap. There's also a whole Bootstrap software repository, which contains various tools for setting up Bootstrap problems, computing the conformal blocks that enter them, and analyzing the results. So it's not too hard for someone new to jump into this game now. Okay, so let me show you some results. I'll start with some older results and work my way towards newer results. So, in three-dimensional CFTs, the first truly exciting result was this plot, which came from studying 4-point functions sigma, 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 like I discussed, and placing an upper bound on the scaling dimension of the first scalar, epsilon, appearing in the sigma, sigma OPE. And so everywhere in this disallowed region, we were able to find this functional or separating plane that essentially rigorously rules out that value of delta epsilon. So everything in this disallowed region is rigorously ruled out by the Bootstrap, but everything in the allowed region may or may not be allowed. So there may or may not be CFTs in this space. We can't say anything definitive. But the exciting thing about this plot is that it has some funny kind of kink in it. There's an obvious discontinuity in the slope of this bound, and actually the location of that kink seems to match onto the known scaling dimensions for the three-dimensional Ising model, described by the Wilson-Fisher fixed point. So that was sort of a first hint that this conformal bootstrap, knows about real CFTs. There may be some CFTs that are particularly easy to solve using bootstrap techniques, and the 3D Ising model seems to be one of them. Okay, so then we get this bound with a kink in it. We ask, can you do better? And it turns out that you can do even better by thinking about 4-point functions involving multiple operators, like both sigma and epsilon. And so if you think about all the crossing relations that you get from 4-point functions containing both sigma and epsilon, then you get a system of 5 crossing relations that you can write down. And if you impose that sigma and epsilon are the only relevant operators in the theory, namely the only scalar operators that have a scaling dimension smaller than 3, then you actually get some closed allowed region right around the Ising the Ising model dimensions shown with this plus. And you can basically isolate the solution corresponding to the Ising model. And by pushing the numerics further, I mentioned way back here that we take derivatives up to some order capital lambda, so we can increase the search space for this functional by increasing lambda, and see how small we can shrink this island by throwing more and more computing power at it. And we can make it quite small. Actually, the sort of best island we can get here requires also scanning over the OPE coefficients involving these three leading operators. So if we sort of make a three-dimensional plot in delta sigma, delta epsilon, and lambda epsilon, epsilon, epsilon divided by lambda sigma, sigma, epsilon, then we get a very, very small region. The point of doing this OPE scan is partly to exclude the possibility of having sort of degenerate exchange operators at the same scaling dimension, but with different coefficients. This sort of inputs the statement that they have a unique value of the OPE coefficient, or at least the ratio. Okay, so this gives us a very small result, which was about 2 orders of magnitude smaller than the best Monte Carlo simulations. Okay, so this best island for the Ising model we obtained about 5 years ago with errors in the 5th or 6th digits. Okay, so what other CFTs can we learn about using these bootstrap techniques? So we've also had a lot of success with the 3-dimensional ON vector models. So thinking about a theory with an n-component scalar field and a quartic interaction like phi I squared. Different values of n are interesting. So the case of n equals 2 is interesting because it describes the superfluid transition in helium-4, or the XY model. The case of n equals 3 is interesting because it describes isotropic ferromagnets. And large n is also interesting because the theory is solvable in a 1/n expansion. Here I'm just showing some experimental data for the O2 model taken aboard a space shuttle mission from the 90s, where they measured the heat capacity of helium-4 as you cross the superfluid transition. And from this data, you can extract fairly precise values of the critical exponents. The critical exponent alpha. Okay, so what can the bootstrap say about the ON model? So we can basically repeat this game that we played with the Ising model. We think about 4-point functions, phi I, phi j, phi k, phi l, where phi is a vector under the ON global symmetry. You can incorporate all the global symmetry information into the bootstrap by expanding the 4-point function in different ON tensor structures, reading off a crossing relation sitting in front of each tensor structure. And you can impose gaps or place bounds in different ON representation sectors. So this bound is showing a bound on the leading ON singlet, delta S, as a function of delta phi for different values of n. So you get a sequence of bounds. And they each have a kink in them at large n. For example, you can see that the kink in this O20 bound matches very, very nicely to this black plus, which is showing the location of the prediction from the large n expansion for the O20 model. And similarly, you see a very nice agreement for O10. Going down to small values of n, you see some error bars here. Those are showing the best, or at least at the time, the best available Monte Carlo or experimental data for those universality classes. So you can see that there was nice agreement. Maybe something funny was going on with the 05 and 06 models, which we haven't really returned to yet. Okay, so you can get these kinks again. The bootstrap seems to know about the ON vector models, and actually you can again isolate the bootstrap solutions by going to a larger system of correlation functions involving the leading ON vector and singlet operators. And here again, we sort of play the same game that we played for the Ising model. We input that phi and s are the only relevant operators in their symmetry representations, and this leads to some closed islands. And recently, we were motivated to try to push these even further for the O2 and O3 models. So actually, our best bootstrap bounds for the O2 model involve a system of 3 external operators, phi I, S, and the leading 2-index tensor, Tij. And using this system of 3 operators, which gives you 22 crossing relations, we could compute a very small bootstrap island shown in the small black region in the middle. This is sort of gives you a sense of how these bootstrap islands has been shrinking over time by considering more correlators and larger derivative orders. And shown in these rectangles are various Monte Carlo determinations. The smallest one is a recent Monte Carlo simulation by Hausenbusch. And this horizontal band here is showing the numbers extracted from this helium-4 measurement. And so this was part of the motivation for us to push these bootstrap bounds further, is that there seemed to be some kind of disagreement between the exponent extracted from the helium-4 measurement and the Monte Carlo simulations. So at the present time, we can basically compute a rigorous allowed region, which seems compatible with Monte Carlo values. So here's a close-up of the bootstrap island compared to exponents extracted from Monte Carlo. You can see that there's basically a beautiful overlap between our two regions. Okay, actually, in order to carry this out, we have to do sort of a similar game as we did for the Ising model. We need to, first of all, scan over the 3 external scaling dimensions, delta phi, delta s, and delta t, and also the OPE coefficients involving these operators. So there are 3 ratios of OPE coefficients that we need to scan over. So that amounts to searching through a 6-dimensional parameter space. And we've come up with various sort of search strategies for mapping out this parameter space that I'm happy to tell you about at the end if there's time. But let me suppress that for now. But the end result is that we can basically map out, some 3-dimensional ball in delta phi, delta s, and delta t space. And for each point in this ball, there's some allowed region in OPE coefficient space that we can try to compute. And by mapping out this allowed region, we get precise determinations of the CFT data for the O2 model. Okay, we've done a similar thing for the O3 model as well. Here's a plot showing the bootstrap island for the O3 model compared to, again, Monte Carlo simulation results. You can again see that there's very beautiful agreement. One question that we were honing in on in our bootstrap analysis was the question of whether, so in the O3 model, you can think about the 4-index tensor phi I, phi j, phi k, phi l, where all the indices are symmetrized. This operator is quite interesting because if you perturb the O3 model by a deformation which preserves a cubic subgroup of the O3 symmetry, for example, if your O3 fixed point came from a theory which lives on a cubic lattice, and that breaks the O3 symmetry down to a discrete cubic subgroup, then that corresponds to deforming the theory by this 4-index tensor operator. And it's quite interesting to know whether this operator is relevant or irrelevant, because if it's relevant, then it means that the theory is unstable to cubic deformations, and any magnet which sits on the cubic lattice would actually be described by a different cubic fixed point rather than the O3 fixed point. So, okay, there have been various studies of this question over the years, all of which point to the dimension of this operator being very, very close to being marginal. So many results show that it's just slightly relevant. There were a few results indicating it could be slightly irrelevant. So this was sort of a question that's a nice question for the bootstrap to ask. So one thing we did is basically search over this island and ask, what is the maximal scaling dimension of this 4-index tensor? We try to maximize the gap until this 4-index tensor. And we designed a special kind of search, which helps us maximize its gap, called a tip-top search. And at the end of the day, we computed an upper bound on the scaling dimension of this operator in the O3 model, which is that it has to be less than 2.99. Okay, so this is basically a proof using the bootstrap that critical Heisenberg magnets are unstable to cubic anisotropy. Okay, so that's sort of an interesting physics result that we were able to extract from this analysis. In the future, it would be interesting to really nail down the dimension of this operator and also put a lower bound on it, but we haven't done that yet. Okay, so maybe I'll pause for a second to see if there are any questions.
David,
Yeah.
Sorry. When you do these searches, the regions that you narrow down are kind of long and thin. Is there any information in the shape of these regions? Or is there any reason why you have more precision across than along?
Yeah, that's a really good question. Yeah, somehow, yeah, there are particular funny directions in scaling dimension space where the bootstrap can really, narrow down the region in those directions. I don't think we understand why that is. That's a good question to understand in the future. I mean, one thing I will say is that when we actually do these searches, we perform an sort of affine transformation in scaling dimension space, which maps the shape of these long, skinny regions into a sphere. So that's actually what we saw over here on the left plot. We performed an affine transformation, which mapped the long, skinny shape into a roughly spherical shape, which helps us do the search more efficiently. But the fact that in the real physical space, it's long and skinny in one direction, we don't understand that. I think that's a good question to think about. Okay, so in the rest of my talk, I wanted to try to show you some results for theories involving fermions. Okay, so I think there are many experts in the audience here on various relativistic theories involving relativistic fermions in Flatland, which is the theme of the conference. I'll just summarize a few facts about them. So of course, there are interesting CFTs involving fermions in 2+1 or 2+1 dimensions. In particular, there are the Gross-Neveu models involving fermions with 4 fermion interactions, which are believed to have a UV fixed point. Or you can talk about Gross-Neveu-Yukawa models, where you have n fermions interacting with a scalar field sigma, and there's a Yukawa interaction, perhaps along with a quartic interaction for the scalar, and these theories are believed to have an infrared fixed point. Of course, there are also variations on these theories involving Lagrangians with multiple scalar fields. So this model I'm writing down here, I believe, is called the Gross-Neveu-Yukawa chiral Ising model, and there is also models with 2 scalars, which would be the Gross-Neveu-Yukawa XY model, and 3 scalars, Gross-Neveu-Yukawa Heisenberg models, and so on. Okay, these theories are interesting for various reasons. So, of course, there's a long history of work on studying these models in a 1/n expansion, going back to work by John Gracie from the early 90s, and other people. And then there are various applications of these models at different finite values of n. So from what I understand, there are interesting applications in the case of n equals 8. Oh, by the way, I should mention that here I'm counting in 2+1 dimensions. The smallest kind of fermion is a 2-component real spinner, which would be a Majorana fermion in 2+1 dimensions. So I'm counting the number of Majorana fermions here. And the case of n equals 8 has possible applications to critical points D-wave superconductors or graphene. In the case n equals 4 has applications for describing spinless fermions on honeycomb lattice or models of gapless semiconductors. I think there are various experts here on these applications. Another interesting case is the case of n equals 1, which I'll talk about first, where you can think about the theory involving, a real scalar field sigma coupled to a real Majorana fermion psi. And this model actually is particularly interesting because it has the fixed point has an enhanced symmetry, which is 3-dimensional curly n equals 1 supersymmetry. So this is the sort of the smallest superconformal field theory in 3 dimensions. Supersymmetry tells you there's a relation between the Yukawa coupling and the Cordic coupling, which can be captured by a theory with a cubic superpotential in superspace. This theory is also, potentially has some applications to real systems. For example, it's been proposed that it might be realizable as something which lives on the boundary of topological superconductors, and work by Grover, Shang, and Vishwanath. So what can the Bootstrap say about these models? So, having extra supersymmetry is very helpful because we can impose the constraints of superconformal symmetry on all our correlation functions, impose that operators live together in supermultiplets. So you can do that in the Bootstrap equations. And the other thing that's helpful is that supersymmetry relates correlation functions involving fermions to correlation functions involving scalars, and dealing with external scalars is easier in the Bootstrap. So we've been able to push this quite far. And by looking at the system of correlators involving sigma and epsilon, this is the same kind of system we used for the Ising model, but also imposing the constraints of supersymmetry, we can make very, very tight determinations of the scaling dimension of the leading scalar sigma, as well as the next scalar sigma prime, which appears above it. So here, these islands are showing the allowed region and delta sigma and delta sigma prime. By the way, I should mention that this theory has a parity symmetry under which sigma is parity odd and epsilon is parity even. So here sigma prime is the second parity odd scalar operator, and you can see that we can determine it to be slightly relevant. Its dimension is 2.88 or so. So the result for this supersymmetric model seems to be nicely compatible with known results from the epsilon expansion. Here I'm quoting a value which was in a paper by Ihrig, Mihaela, and Scherer. So this is sort of an interesting playground for the Bootstrap, where it's another model where we can learn very, very precise data using Bootstrap methods. Just one curiosity that I wanted to mention, which has been keeping me up at night, is that so supersymmetry imposes that the OPE coefficients involving sigma and epsilon are related to each other. In particular, they're a particular function of the scaling dimension of sigma. It's a certain rational function that you can work out using supersymmetry. And if you parameterize this ratio of OPE coefficients as the tangent of some quantity theta and ask, okay, what does this Bootstrap island tell you about theta? For some reason, which we don't understand at all, it has to be very, very, very close to 1. So we get this funny value that the ratio of OPE coefficients is almost exactly the tangent of 1. Maybe it's 1.0001, but 1 is still within our error bars, which corresponds to the very, very upper right tip of this region. And so it's sort of it might just be numerology, but it's worth thinking about whether there could be any meaning to this relation. Okay, so that's what we've been able to do with the n equals 1 Gross-Neveu-Yukawa model. What about larger values of n? So of course, there's a whole, as I mentioned, there's a whole history of computing the large n expansion in the Gross-Neveu-Yukawa model. Here I'm summarizing various operators in the theory and the orders that are known in the 1 over n expansion. So for example, the scaling dimension of psi is known to 1 over n cubed. The scaling dimension of sigma is known to 1 over n squared. And similarly for the dimension of epsilon. The scaling dimension of the 2-index symmetric tensor under ON symmetry psi I psi j, I think is only known to order 1 over n, but I could have missed something in the literature. And there are various other higher operators that are sort of interesting for us to know about, particularly in the bootstrap when we impose gaps in the spectrum that we want to be compatible with, for example, these large n predictions. One operator I'll highlight here is the sigma prime operator, the second parity odd scalar, which you could think about as being like sigma cubed in a perturbative description. This operator at large n becomes exactly marginal. This is closely related to the deformation that Daniel Leidom was discussing this morning, where he thought about Gross-Neveu models perturbed by a 6 fermion interaction. This is in the Gross-Neveu-Yukawa description. This is like the 6 fermion interaction. And then at finite n, we know that there's a positive correction, so it becomes slightly irrelevant. On the other hand, over here in this n equals 1 case, you can see that it becomes slightly relevant. Scaling dimension is 2.88. So there's some interesting transition where it goes to being irrelevant and then comes back down to being relevant. So actually, this operator seems to play an important role in the bootstrap analysis for us. Okay, so what can we say using the bootstrap? So I'll show you a few older results, and then I'll show you some brand new hot off the press results. Okay, so here's a bound which we can compute using the bootstrap, applied to 4-point functions of the fermion psi I. And for each value of n, we can place a bound on the leading 2-index tensor operator, sigma t. This is leading parity odd 2-index tensor, which is like psi I psi j. So you can see there's sort of a curious structure here. So for n equals 2, we get some curve. And then at larger values of n, you have the curves basically follow the n equals 2 curve and then branch off at some point. And the other interesting fact about this plot is that the location at which it branches off, at least at large n, seems to match nicely to the large n predictions for these scaling dimensions. So this is, I think, a hint that the bootstrap knows about these Gross-Neveu-Yukawa fixed points, and they might also be relatively easy to solve using the bootstrap, similar to the ON models. Okay, and you could conjecture that, say the n equals 4 model sits up here, the n equals 2 model maybe sits up here, but that's a conjecture at that point. You can also get sort of an interesting exclusion plot in the delta psi, delta sigma plane, where if you assume the sigma prime operator is irrelevant, larger than 3, then you sort of carve out these really interesting lower bounds, which have a wave-like structure. And at large n, they sort of have a tip that matches nicely to the large n predictions. And at small values of n, you can compare sort of where this tip is to predictions in the epsilon expansion. And you can also see that there's pretty good agreement. So, our sort of conjecture at the time, this was a study we did 4 years ago, was that basically the upper kinks that you can see in these waves are going to converge to the Gross-Neveu-Yukawa fixed points. And we could use their locations to get some bootstrap estimate of the CFT data. And actually, so I'm going to flash a couple plots from a nice paper by Ihrig, Michaela, and Scherer from 2018, showing a comparison between bootstrap results and results from other methods, including large n resummations of the epsilon expansion, functional renormalization group techniques, and Monte Carlo techniques. So this left plot is showing the exponent associated with the scalar, what I'm calling sigma. You can see there's quite good agreement across all of the techniques, including these bootstrap estimates from the kink locations. Similarly, you can see there's nice agreement for the exponent associated with the fermion psi. So that was actually very reassuring that we were sort of on the right track. On the other hand, we also tried to get some bootstrap estimates for the other operators like delta epsilon, the parity even scalar, which is associated with the critical exponent nu. And to do that, we sort of used the non-rigorous approach called the extremal functional method, where you look at this functional that you apply to the bootstrap equation and read off the locations of its zeros. And at least in the past, in like the Ising model and ON models, those zero locations have given us a very precise picture of the higher spectrum. So we thought it might work here too, but it's a non-rigorous approach. And it gave us some values of the new exponent, which were quite different from other methods that you can see in this plot. So that was sort of an open question, you know, why did we get this discrepancy and how can we do better? So let me show you. Yeah, go ahead.
5 plus 5. So 5
okay, thank you. Yep, thank you. Great. So let me show you some brand new results from the Bootstrap for Fermions, and then I'll wrap up. So our sort of state-of-the-art computations for the ON Gross-Neveu-Yukawa models involve an even larger system of correlation functions, psi I, sigma, and epsilon. This gives 38 crossing relations after you allow for all sort of 4 ON tensor structures and Lorentz tensor structures involving the fermions. And in this system, we basically are imposing various gap assumptions motivated by these large N expectations, and search for allowed points in the 6-dimensional space involving the 3 scaling dimensions, delta psi, delta sigma, delta epsilon, and also the 3 ratios of OPE coefficients involving these operators. So it ends up being very similar to our search in the O2 model. And so now we're able to actually get closed bootstrap islands for the Gross-Neveu-Yukawa models. And so here's our preliminary, not yet published island for the n=2 Gross-Neveu-Yukawa model. As I said, we impose various gap assumptions. I'll highlight here that we impose a pretty big gap in this operator delta chi. Chi is the leading sort of parity, you might call it a parity odd fermion. So it's, if you think about the equation of motion in the Yukawa theory, then the equation of motion tells you that the derivative of psi is related to sigma psi. So the operator sigma psi is really a descendant of sigma. So there's a big gap in the spectrum of conformal primaries in that sector. So that's reflected in this big gap that I call delta chi up here. And also here we were being a bit conservative and imposed the dimension of the sigma prime operator is bigger than 2.5, though it's plausible that it's still bigger than 3. But so making those gap assumptions, we can get these islands. And now we can learn about the CFT data using a basically rigorous approach and constrain delta psi, delta sigma, and delta epsilon. You can see that in this island, the value of the 1/nu exponent here, now we're getting 1.25. If I go back to this plot I showed you earlier, 1.25 is way up here, basically right on top of the epsilon expansion and FRG results. So basically, yeah, I think we've completely resolved this discrepancy. These points are nonsense for some reason that we didn't quite understand, but the real bootstrap result should be right up here. Okay, and okay, so here's showing what happens to the allowed region when we increase the gap in sigma prime up to 3. You can see that there's actually quite a bit of sensitivity to the sigma prime gap, and we can get a tighter determination from that. We're still pushing these to higher derivative orders, so these are going to shrink shrink even further. Maybe one thing I'll flash is that, because we know the dimension of sigma prime at large n, and we know its value at n equals 1 from this supersymmetric Ising story to be 2.88, we can basically do some kind of two-sided Padé approximation of the scaling dimension of this operator to try to get estimates at intermediate n. And these are the curves we came up with. So if you believe these curves, then this operator should be irrelevant all the way down to n equals 2. But I think it's sort of an interesting task for other methods to try to confirm this, learn more about the dimension of the sigma prime operator, and maybe with the epsilon expansion or other techniques. Okay, we can also get now islands for the n equals 4 Gross-Neveu-Yukawa model at sort of a similar level of precision. I'll sort of highlight that here we get a very, very precise determination of delta psi or eta psi at basically at the 3rd to 4th digit, less precise determinations of the other scaling dimensions, but here they're roughly at the 2nd digit. And these we haven't, and here's a similar plot for n equals 8. We haven't pushed these very far yet, so we're currently working to push them to much higher derivative order and shrink the islands further. Okay, let me just briefly say one thing about one other application, and then I'm done. Another interesting target for Bootstrap techniques is 3-dimensional QED coupled to some number of fermion flavors. This is a bit tricky from the Bootstrap perspective because you can basically only use gauge invariant operators like psi bar psi or f mu nu, which dualizes to a current, the topological current. And so that makes it sort of hard to have any direct access to the gauge group, and it's not so easy to distinguish QED from QCD just by thinking about gauge invariant operators. There was some progress in the Bootstrap in work by Chester and Pufu about 5 years ago, which looked at monopole operators in QED. And we know something about the monopole operators at large n. So for example, the leading monopole, which has charge 1/2, has a scaling dimension which scales linearly with n. And we can use this formula to get some estimates at finite values of n. Okay, there's lots of other data known about the large n spectrum. And so we sort of have an ongoing project to try to learn something about small n QED3 using these large n estimates as a guide. We've been focusing on the case of NF equals 4. And so I won't dwell on that slide. In the older work of Chester and Pufu, they basically saw that if you place a bound on the charge 1 monopole as a function of the charge 1/2 monopole dimension, the bounds that you get are close to being saturated by the large NF predictions at NF equals 4. And actually by isolating that first charge 1 monopole, you can carve out some kind of peninsula. So we've been trying to improve the situation even more. So I'll just flash a slide and then I'll be done. The situation isn't perfect. We haven't quite understood how to isolate the scaling dimension of the leading monopole operator using Bootstrap techniques. But what we have understood is that if you input the scaling dimension of the leading charge 1/2 monopole, here I've input its value as 1.02, which is roughly the large n prediction applied to NF equals 4, then you can get an island in all the other CFT data after imposing some gaps motivated by the large n spectrum. So this is all work in progress. We're making some progress. It seems like that if you input one piece of large n data, that you can predict everything else, but it's not a super precise prediction yet. Okay, so this is something we're actively working on. So, okay, so that's all I wanted to tell you. So there are lots of interesting directions for the Bootstrap. We can try to find islands for other interesting CFTs, like these variations on the Gross-Neveu-Yukawa models, the XY and Heisenberg models. We're really, actively working to try to understand how to isolate gauge theories. And there's a whole sort of interesting zoo of superconformal theories out there that we could tackle with bootstrap techniques. To push on these directions, it's sort of proven helpful to go to larger systems of bootstrap equations, think about mixed correlators, perhaps involving spinning operators like currents and the stress tensor, which in turn requires improving our algorithms and software tools. And there's also an fascinating interplay going on right now that I didn't have time to tell you about between numerical bootstrap and analytical approaches to the bootstrap equations. And ultimately, I think we can do a better bootstrap by combining insights from the analytical bootstrap into the numerical algorithm. So that's another direction to push. All right, so thank you very much for your time, and I'll stop there for questions.
Okay, so thanks, David, and I'll do the corporate hand clap. Okay, so we've got a few minutes for some questions. So I think Simon had his hand up first.
No, sorry, I didn't. I was trying to clap, but I'm
I just realized
good with Zoom.
Sorry, yeah. Okay, Vieri's got a question. Thank you, Vieri.
Yes, I think you are speaking about quantum electrodynamics in 3 dimensions with bosons 1/k², right? So for graphene can be used also a sort of simplified in which the boson is 1/k. In that case, should be a line of fixed points and anomalous critical exponents. So I was wondering if you can apply this bootstrap also to this case. So QED3, but with the boson 1/k, because you integrate one. I mean, that's the correct model.
You're talking about QED3 coupled, an abelian gauge theory coupled to scalar field rather than.
Yes, but not with the boson propagator, not 1/k², but 1/k. So it decreases the infrared divergences.
Mm-hmm.
Because you integrate 1/1 coordinates, right? You have the photon in the space, but the graphene is in the plane. So you integrate over 1 K0, K3, let's say, then you get 1/k instead. So the theory is a different, is a line of fixed point in that case. So I was curious to know. So for graphene, that would be the right model. So I was wondering if there are possibilities to use this conformal bootstrap for cases in which you have lines of fixed point.
Yeah, so that's yeah, there have been various cases where, so I think the answer is yes. I haven't thought about the particular situation you described, but for example, there's been a bootstrap attack on 4-dimensional n=4 super Yang-Mills theory, which has a line of fixed points, and there they can study, try to study the line of fixed points in that, the conformal manifold.
So in that case, you can consider a line. So you have really an exponent which depends on the parameters. I see.
Yeah, that's right. Yeah, so that's something that can happen. There was also some work by Connor Behan describing the bootstrap applied to conformal manifolds, lines of fixed points. So yeah, there's been some work along these directions. Also if you do the bootstrap in the 2 dimensions, thinking about O2 symmetric theories, you can see the Kosterlitz Taulus line of fixed points in that context. So in general, yes, if you have a line of fixed points, you'll see some whole line of allowed region in the bootstrap solution space rather than a closed island, which is shrinking to a point. So that, in some sense, makes it trickier. Oh, I should have mentioned another example where there's a line of fixed points is in the long-range Ising model. There was also some bootstrap studies of that family of fixed points. Anyway, so I think, the shorter answer is, in principle, that's a situation that could be studied with the bootstrap. So.
Okay, we've got another question for Lucas. Now we'll move on to the next talk. Thanks, Lucas.
So any chances to study some non-relativistic fixed points? I mean, to do something similar for non-relativistic, say the cubic fixed point in the O3 Heisenberg model?
So let's see. So one can study the relativistic fixed point with a cubic global symmetry. So we're a cubic subgroup of the O3, there's a cubic subgroup of the O3 global symmetry, but you still have a relativistic Lorentz space-time symmetry. That's a situation that has been.
That's right. I see. Okay, that's still relativistic. I see the point.
Still relativistic.
But I mean, having some relativistic symmetry is required.
Yeah,
right?
that's very helpful for us. So if you go to a non-relativistic situation, then you lose some of the power of conformal symmetry, and maybe there's something you can do, but the bootstrap becomes much less constraining. For example, you start getting multiple 3-point structures that are allowed rather than a unique 3-point structure between conformal primaries, and it becomes much more complicated.
Yeah, I see. Okay, thanks.
Tony, if it's a quick question, we can have it, and then we have to move on to the next talk.
Well, I was just wondering, David, can you tell us a little bit more about the prospect of exploiting the conformal bootstrap for gauge theories? You indicated a couple of points in your outlook. Is there a chance that we, say, can learn something about, I don't know, Banks-Sachs fixed points, or as you mentioned, 3D, scalar QED, superconductivity, phase position, material?
Yeah. So, right. So actually, there was some progress on 3D scalar QED that I didn't mention. That there were some other groups that basically found some set of bootstrap assumptions that seem to isolate 3D scalar QED theories, though not very precisely yet. So that's a theory where I think real progress will be made in the near future. For Banks-Sachs type theories, in say 4 dimensions, there's a lot of interest in the bootstrap community. There are various 4-dimensional bounds that people have computed which apply to these theories, but they're not very constraining yet. We recently sort of saw some hints of some kinks in these bounds, which seem to relate to fermion bilinear type operators in large N Banks-Sachs type theories, but the connection we haven't made very precise yet. Basically, my feeling is that in order to really make contact with those theories, we need to incorporate the full global symmetry information, which in particular means that we should incorporate the SUNF cross SUNF currents of these theories as external operators in the bootstrap. And then when you do that, you'll start getting access to 3-point functions of currents which encode to Hooft anomalies. And that's sort of one real way you can start inputting some knowledge of the microscopic physics into the bootstrap setup. So that's my feeling, is that to really make contact with those theories, we should include currents and maybe the stress tensor, all as external operators in the bootstrap setup, which hasn't. People are starting to do it, but it's right now it's at its infancy in 4 dimensions. So I think that's the direction that I would push on to make more contact with Banks-Sachs theories.
Okay, thanks, David. So I think we move on to the next talk. Thanks, David, for that excellent talk of another one of our techniques we use nowadays. So if Joseph is around, can you share your screen, please?
Yes.
There you are. Okay, so
Can you see it?
can see it? Yeah, do you want to put it in slideshow? Yeah.
Yep.
Okay, so we next talks from Joseph on QED condensed matter in 3 dimensions. Thanks, Joseph.
Okay, so first of all, I'd like to thank the organizers for inviting me to this very nice workshop. So the work will be about a bit of a condensed matter perspective on QED3 that we've heard a bit about from David's talk and then in some other talks. And so I'll focus on kind of 2 aspects. One will be how this can be applied to describe quantum phase transitions. And then I'll talk about also possible role of instanton zero modes to describe certain broken symmetry phases in these systems. Okay, so the talk in a sense will be about lattice QED. So what is lattice QED? So it was originally proposed by Wilson and others in the early 70s as a model to understand non-perturbative aspects of continuum relativistic gauge theories, like the Standard Model, where among other fields, we have direct fermions interacting with gauge fields. And so this was first written down for a QED, so for a U1 gauge field, but then eventually for QCD, where we have non-abelian gauge fields, because the real goal was to understand non-perturbative physics like quark confinement and how this can arise from the strong interaction. And so essentially what we have in these theories are fermions that live on sites, and gauge fields live on links of some lattice. So you can think of those as pyrals or kind of Aharonov-Bohm phases that are picked up when the fermions hop between neighboring sites. And the lattice in this sort of particle physics context comes from discretizing space or space-time as a mathematical approximation. So in condensed matter physics, we kind of turn this idea a bit on its head. We start from having a lattice. So having a lattice is really the natural starting point because, for example, we'll have a crystal structure if we have a solid state material, or we can have an engineered optical lattice if we are interested in optical atom systems. And so we start from a lattice. So the question is, where do we get relativistic fermions? And also, where would we get dynamical gauge fields if we're going to arrive at some lattice QED3 description? So we know that this can arise as an effective low energy description of certain strongly interacting quantum many-body systems, in particular in reduced dimensions. Okay, so in this talk, so this will be in Flatland, which is again the focus of the conference. So we'll have 2 spatial dimensions and 1 time dimension, so it's 3 space-time dimensions. Okay, so for the most part, we're interested in the quantum many-body system living in 2 space dimensions. So time is a continuous variable. We're doing quantum mechanics in 2 spatial dimensions, but in some cases, it's also helpful to discretize the 3rd dimension, and then we can think of this as some classical, if you will, 3-dimensional Euclidean lattice gauge theory. Okay, so let's look at a couple examples. So for example, in the early 2000s, there was one approach to describing the pseudogap state of the high TC superconductors as the D-wave nodal quasi-particles, which are direct fermions, interacting with gauge fields that would represent vortex fluctuations, in this case, in the pseudogap state. Then in a somewhat related context, there is a description of spin-liquid phases of 2D quantum antiferromagnets. So these are phases that are essentially paramagnets. There's no magnetic order, but they are quantum disordered as opposed to being kind of trivially thermally disordered. So this was kind of proposed early in the high TC context, but also more recently, there's a lot of interest in the frustrated magnetism, in particular on the Kagome lattice, okay, which is a lattice of corner sharing triangles, because there's a belief and also some experimental evidence that this, if we have local spin-and-a-half moments on this such a lattice, then at very low temperatures, at 0 temperature, we can maybe realize a so-called Dirac spin-liquid state. Okay, it's a very exotic quantum disordered state of matter. And the low energy description of this is in terms of fractionalized spin-on excitations, which are emergent particles that carry spin but do not carry electric charge. So they are kind of neutral fermions called spin-ons, which have these fractionalized quantum numbers and have a relativistic Dirac dispersion, and then furthermore interact with some emergent gauge field, which is a U1 gauge field in the simplest context. Okay, so we get essentially this kind of continuum QED theory arising in this context. And even more recently, there's been various proposals to, in fact, kind of directly engineer lattice QED3 using ultracold atoms and optical lattices. Okay, so in this case, you start from both fermions and bosons, so just ordinary fermionic atoms and bosonic atoms. So the fermions live on the sites, let's say, of some square lattice, and the bosons live on the links. So there's no gauge symmetry to start with, but then there's a gauge constraint that is applied dynamically by introducing some large energy penalty for configurations that would violate some Gauss law, some local gauge constraint. Okay, so in fact, in 1+1 dimension, this was realized experimentally, some small systems, but at least there is a proof of principle that this can be done, basically some kind of lattice Schwinger model. And of course, 2+1 dimensions is more complicated, but there's some encouraging progress. For example, there's some very concrete experimental proposals of how to realize this. And so for all these reasons taken together, we would like to, from a condensed matter standpoint, at least, to theoretically understand the phase diagram of lattice QED3 on various lattices. Of course, it's intrinsically interesting from a high energy perspective, but for condensed matter, these are effective models describing physical materials. Okay, because this lattice QD3 phase diagram could impact the physical phase diagram of all of these condensed matter systems. So it's a difficult, strongly coupled problem. There's no analytical solutions except in some limits, but it's definitely worthy of investigation. Okay, so the outline of the rest of the talk will be as follows. First, I will focus on this U1 Dirac spin liquid that I briefly alluded to here, and briefly explain how it might arise from lattice QD3 in some conformal limit, okay, which is the conformal QD3 fixed point that David essentially mentioned, that shows up in the large N limit, and assuming that relevant operators like monopole operators and maybe some 4 fermion operators are irrelevant, which will be the case in the large N limit. Then I'll focus on 2 main subjects. The first part will be the longest, which will be essentially trying to describe various universality classes of zero temperature transitions out of this conformal QD3 phase, out of this Dirac spin liquid phase, and how these might differ from conventional universality classes of non-fractionalized states of matter. So here the methodology will be either perturbative expansion using the epsilon expansion or non-perturbative, but expansions in terms of a small parameter, namely the large N expansion. So in this case, we won't discuss monopole operators. And then in the latter part of the talk, which will be a bit shorter, I'll try to argue that in the case of QD3 with massive fermions, we find that a monopole or instantons of the spacetime picture can lead to interesting symmetry breaking effects. Okay, so before I delve into the technical part of the talk, I just want to thank my collaborators. So this was a fairly large collaboration. So Rufus Boyack was a postdoc with me. He's now in Montreal. John Gracie, one of our organizers, performed various high-order large N computations. Chen-Hung Lin was also a postdoc with me. Peter Markert, we heard from him earlier today, and Nikolai Zerf was a postdoc in Berlin who performed high-order epsilon expansion loop calculations. And Ahmed Ryan was a student with me who's now in Toronto. And the work is in various papers published. And just want to shamelessly advertise that a lot of the topics I'll be talking about today from the point of view of quantum criticality, we wrote a short review. So with Rufus and then my current student, former student, Gennady Ryzhakov, who's also part of this meeting. Okay, so the starting point will be a particular incarnation of lattice QD3 that was studied a few years ago, 2 years ago, by a very nice numerical quantum Monte Carlo study by Fakir Assad and Jiang Meng and collaborators, where they consider the following model. So it's on the square lattice. And we have fermions, lattice fermions with this annihilation operator C. And we have NF flavors of these lattice fermions. So if you want the number of 2-component Dirac fermions in the continuum formulation that we'll get to in a second, you need to multiply this number by 2. Okay, and these fermions are coupled to this rotor variable that lives on the links of the lattice. And then there is this first term here, which depends on this conjugate sort of angular momentum operator conjugate to the rotor variable. So you can think of this as some kind of electric field squared term in the Maxwell Hamiltonian. And this is the cosine of the lattice flux, the flux per plaquette of this this rotor variable here. So you can think of this as the analog of the V squared term in the Maxwell Hamiltonian. Okay, and so they study this the phase diagram of this model at zero temperature as a function of the number of fermion flavors on the lattice, and also the strength of this coupling J here, which you can think of as tuning the strength of the gauge fluctuations in this problem. Okay, so what they find first of all at small j is that we get this essentially this conformal QD3 phase with massless relativistic Dirac fermions emerging at low energies coupled to a dynamical UN gauge field. Okay, so the way this arises is that first of all this magnetic coupling here to minimize the energy would rather have a pi flux per plaquette, and this converts your square Fermi surface at half filling to a Dirac dispersion, as we heard in Sandro's talk earlier in the workshop, and this will produce for you relativistic fermions in the band structure. Okay, so that's how you get your relativistic fermions. But now, in addition to this static flux background, this electric field squared term here will make essentially this this gauge field fluctuate, and then we'll have an emergent dynamical UN gauge field that couples these relativistic fermions. Okay, so in the condensed matter context, this was known as the pi flux phase, introduced by Ian Affleck and Brad Marston. in the early 90s. And so the signatures of this phase is that it should be a power law correlated phase. Because in fact, the prediction is that it's a conformal field theory. So all the correlation functions decay as a power law with universal exponents. And indeed, this is what is observed numerically in the Monte Carlo. Okay, so for example, you can compute the spin-spin correlation function or correlation functions of some bond operators, and you find power law correlations that are predicted by this sort of conformal field theory description. Okay, so this is what they refer to as this U1 deconfined phase, and it seems to appear for all these fermion flavors. Okay, so this would be kind of a proof of principle, numerical proof of principle of the existence of this Dirac spin liquid. And then they keep increasing this coupling here that controls the strength of the gauge fluctuations. And what they find is that there will be a phase transition to a broken symmetry phase. Okay, so here, this conformal phase here does not break any symmetries. In fact, it has emergent symmetries. But if the gauge coupling is too strong here, then we get a confined phase with a broken symmetry. So for two flavors of lattice fermions, which you could think of as a spin and a half degree of freedom, we get an antiferromagnetic Néel phase, where spins have this kind of checkerboard pattern. So this we can understand fairly simply from the point of view of the infinite J limit of the models. You can use strong coupling perturbation theory, and you will show that this model, in fact, reduces to the nearest neighbor Heisenberg model on the square lattice, which we know orders antiferromagnetically at zero temperature. So from the point of view of these direct fermions, they acquire a mass. They're being gapped out. And what is interesting is that in the numerics, there seems to be not only a phase transition, but it seems to be a continuous phase transition. Okay, so there's no jump in the order parameter. So there seems to be evidence of critical phenomena here. And so we'd like to understand what is the universality class of this transition. Okay, so what we'll do is we'll try to construct some effective continuum description of this transition, sort of thinking in a kind of Lana Ginsburg Wilson way about this problem. So we need to incorporate the ingredients of the disordered phase, the symmetric phase, which is QD3. So we're going to have the right number of flavors of here 4-component direct fermions, and a Maxwell term for the fluctuating gauge field. So this will describe here our deconfined phase at weak coupling. And then we're going to have an antiferromagnetic phase. So this is a collinear antiferromagnet. So we'll have a broken O3 symmetry. So then we naturally introduce an O3 vector, which describes the broken symmetry. And so this by itself would just be the O3 vector model that David mentioned earlier in his talk. You might think that we're going to simply recover the O3 Heisenberg universality class, okay, because that is the relevant broken symmetry. But in fact, because there's an allowed Yukawa coupling between the O3 vector and this fermion bilinear that has the same symmetries as this O3 vector, in fact, we'll see that we get a different universality class. Okay, so we can formulate this theory here. This scalar mass here is the relevant parameter that tunes through the transition, and then we can try to explore critical properties using various analytical techniques, for example. Okay, so the first thing we did was to look at the 4 minus epsilon expansion. So the model has an upper critical dimension of 4, and so we simply do the epsilon expansion. So first of all, if we only consider the scalar part of the scalar sector, then we will recover the well-known O3 Heisenberg Wilson-Fisher fixed point. However, if we turn on the Yukawa coupling, then that is destabilized in favor of the chiral Heisenberg Gross-Neveu-Yukawa fixed point. So that is the same universality class as the semi-metal to antiferromagnetic insulator transition in graphene. But then finally, if we turn on the gauge coupling, then this Heisenberg Gross-Neveu universality class is further destabilized in favor of a new O3 universality class, which we dub the Heisenberg QD3 GNY universality class, where we have non-zero couplings for all 3 couplings: the scalar, self-interaction, the Yukawa coupling, and the gauge coupling. Okay, so in the language of Daniel's talk, even though these are abelian gauge fields in 3 dimensions, and slightly below 4 dimensions, this would be the kind of fully interacting fixed point here. Okay, so the idea is that it's a O3 transition, but the paramagnet we start with is not a trivial paramagnet. It's a fractionalized paramagnet, and so we have these gauge field fluctuations. And also these fermionic gaps as degrees of freedom that change the universality class from kind of a purely matter theory to a matter gauge universality class. Okay, so we can this we did sort of at by hand at one loop, but then we can push this further. So here Nikolai and Peter did the heavy lifting for the for loop calculations, and John the heavy lifting for the higher order 1/n computations. We have various plots, so similar to what Peter talked about earlier. So these various Pad-Avery summations. So for higher number of fermion flavors, there seems to be relatively good agreement. For smaller numbers, there's not good agreement. The hope is that eventually the quantum Monte Carlo will have enough accuracy to have reliable exponents near criticality that at least we can compare to see if we're in the right ballpark. So that's left for the future. But there's one so besides the sort of quantitative numerical predictions, there's one qualitative prediction that hopefully could be seen earlier, even if we don't have high numerical accuracy for the values of the exponents that I'd like to briefly discuss here. So if we think first about the symmetric phase, which is this U1 deconfined phase, there is the prediction that there's an emergent flavor symmetry. Okay, so we get these relativistic direct fermions. There's 4 two-component direct fermions. So there's an SU4 flavor symmetry, which implies that in fact there's 2 different operators in the theory that have different physical interpretations. One is in terms of antiferromagnetic correlations. The other one is in terms of bond or valence bond solid correlations that because of this emergent symmetry should have the same scaling dimension. They should decay with the same exponent in this U1 deconfined phase. Again, in the large N expansion, this power can be computed, and indeed, numerically, it's seen that these 2 correlations fall off with the same exponent, and it seems to agree quite well with the large N prediction. Okay, now our prediction is that if you move towards this quantum critical point between the disordered phase and the antiferromagnetic phase, the Yukawa coupling now will break this flavor symmetry, because the flavor symmetry has essentially it's a 4 equals, if you will, 2 plus 2, where one of the factors of 2 is the spin degeneracy, and the other factor of 2 is the value degeneracy. Okay, but the Yukawa coupling will remove the degeneracy because we couple only to the spin bilinears. So the prediction is that the correlations for the antiferromagnetic order parameter should be strongly enhanced. In fact, we have a divergence in stability simply because we have a second order transition in this ordering channel, but the valence bond fluctuations will remain power law, but they will not diverge in momentum space. Okay, and so this big qualitative difference between the correlations, hopefully that can be seen fairly soon in the numerics in future quantum methodical simulations. Okay, so now let's go back to the numerics again. So now let's consider an increased number of fermion flavors. Okay, so for 2 flavors, there is this Néel state, but what is found in the numerics for all flavors studied beyond 2, the first transition is towards not a magnetically ordered state, but towards a valence bond solid ordered state. Okay, so this is a state where you will form nearest neighbor flavor singlets. So you do not break this any of this flavor symmetry, but you will break the lattice symmetry of the problem. Okay, you break the point group symmetry by forming this kind of columnar VBS state. Okay, and so that's the plot of the dynamical structure factor and the ordered phase. So there's a large static peak reflecting the presence of this static long range order at a certain ordering wave vector, and then there's a gap to excitations. Okay, and this is for, let's say, 8 fermion flavors. So again, numerically, it seems that the transition is continuous, and so we would like to understand the universality class of this transition once again. So again, we need to formulate what is the proper critical theory in the long distance limit. And if we do so, again, we will have in the symmetric phase the right number of massless fermion flavors. And now we need to identify the correct order parameter. Okay, so this is the Z4 symmetry. It's a discrete symmetry that's being broken. So this you can express this by considering a complex scalar order parameter, but with a Z4 clock anisotropy. Okay, and so what you would have, in fact, is the so-called chiral XY QD3 Gen Y model, which in fact is equivalent to the model that's well known in the particle physics literature, the Nambu-Jono-Lacinio model, but with minimal coupling to a human gauge field. So there's this Yukawa coupling. In principle, we have this clock anisotropy, but we can show that in the large N limit, this anisotropy is irrelevant, and so we have an enhanced O2 symmetry. So this is why this valence bond solid transition at criticality, in fact, is the broken symmetry is an O2 symmetry. Once again, if we look at the lowest order and the large N expansion, which we did by hand here, then we find again a new O2 universality class, which differs from the 3D XY universality class and also the chiral XY universality class due to the presence of a finite gauge coupling. This can be pushed further. So this we studied this at higher orders in large N expansion and also up to four loop order in the epsilon expansion. And there was some nearly concurrent work by Lucas Janssen and Michael Scherer, where what is fine is again the same idea. So you have the scalar Wilson-Fisher universality class, and then this fermionic universality class that are both destabilized in favor of this gauged universality class that is novel. And again, we can show that in the epsilon expansion, also this anisotropy is irrelevant at criticality, so we have an enhanced O2 symmetry. Okay, so in a sense, all of this from the point of view of spin liquid physics can be put under this umbrella of competing orders. So this is a perspective that was put forward a long time ago in the frustrated magnetism context. So the basic idea advocated by these authors was that this there's all these slow, slowly fluctuating orders in this conformal phase in this ultra spin liquid that, given the chance, could form long-range order if sufficiently perturbed away from the conformal fixed point. Okay, so we saw, for example, that there is this Néel order that indeed can be realized if we have sufficiently strong gauge fluctuations on the lattice. The transition is in this Heisenberg QD3 GN universality class that I mentioned. We can drive this spin liquid towards a valence bond solid phase. This is through again a novel type of XY universality class in 3 dimensions. So in this case, both of the resulting phases that you obtain are confined phases that have a broken symmetry. Okay, but you could ask, is it possible to get another fractionalized phase that is, let's say, also a spin liquid, but that is distinct from this Dirac spin liquid? So in principle, this can indeed happen. The one scenario we explored was suppose that these fermions develop a mass dynamically, but that now this is something like a superconducting mass, or a Majorana mass, if you will, that will spontaneously Higgs the U1 symmetry of the gauge theory. Okay, so this, from a kinetic matter standpoint, would mean that you break the gauge symmetry from U1 to Z2. The fermions are gapped. You get a fully gapped Z2 lattice gauge theory, or yes, at low energies. So what you get is Z2 spin liquid, a gap spin liquid. And the criticality we showed is in a new kind of Higgs QD3 Gen Y universality class. It also has an O2 symmetry, but really this O2 symmetry now is the U1 symmetry, is the gauge symmetry. So there's no broken symmetry, but there's a Higgsing mechanism taking place. And at least if there's sufficiently many fermion flavors, then we do have a stable fixed point describing this universality. And another possibility is that you get a gapped spin liquid that breaks time reversal spontaneously. So this is yet another type of mass that can be turned on in the energy physics literature. This would be an SUNF a singlet mass that breaks parity and time reversal. And so at low energies, what you get is again a gap theory, but if you integrate out the fermions that become massive, it's a topological theory. So it's a transimmons theory, a level 2 transimmons theory, which implies that you have some kind of chiral topological order with on a manifold with boundary, you would have chiral edge states. So this is the Kalmayer-Laughlin spin liquid discussed in the frustrated magnetism literature. And again, there's another type of universality class here. The broken symmetry is a time reversal symmetry. So it's a Z2 symmetry. So we have an Ising, again, a gauge version of the Ising GNY universality class that was discussed by David. So Lucas Janssen was the first to study this. And then there's some 3-loop computations following up by Michael. And then we did some 4-loop simulations, calculations also to study this universality class. Okay, I think I will skip this in the interest of time, and I will go to the last part of the talk, which will be shorter, which will be the following. Okay, so so far I've assumed that the gauge field is effectively non-compact. So we know that on the lattice we can have monopoles or instantons, and I've assumed that at these critical points, the number of fermion flavors, for example, is large enough that the compactness of the gauge field does not play a role, and we can work with these continuum gauge theories and, for example, use these perturbative expansions where monopole operators do not play a role. Okay, so in the remaining part of the talk, I would like to talk about possible effects of these instantons for the physics of these kinetic systems. Okay, so this is work done really by my student Shankar, who is also part of this workshop. And I'll just say a couple things, but for a fuller account, I encourage you to go talk to him, see his poster in the poster session. Okay, so the starting point to motivate the theory that we'll write down is another kinetic system, slightly different one, that was considered in this paper by Berkeshly and McGreevy a couple of years back, where the motivation is, let's say, bosonic ultracold atoms in some optical lattice, okay, which we'll take to be, let's say, the honeycomb lattice. So we have bosons on the lattice that have a global U1 symmetry. And so in kinetic physics, we often use these parton decompositions as a way to access exotic phases that are difficult to describe in terms of the original degrees of freedom. Okay, so in this approach, we will write this bosonic operator as a product of two fermion operators, psi1 and psi2. And when we do this, we immediately realize that there is an emergent gauge symmetry because you could rotate, for example, psi1 and psi2 by opposite U1 phases, and this physical operator remains gauge invariant. Okay, so we'll say that there's an emergent U1 gauge symmetry, and so we'll try to write down a theory of these fermions that describes the phases of these bosons. Necessarily, that theory of fermions must have a U1 gauge symmetry, where in this case the gauge charge has opposite sign for these two fermions. Okay. What these authors argue is that this is a convenient way of predicting various exotic phases that these bosons can find themselves in. Okay, so what we do is basically some kind of Gedanken experiment, or some kind of mean field ansatz, where we suppose that these fermions will form a particular kind of weakly coupled state, the band structure, and then we ask what this corresponds to in terms of the bosons. Okay, so for example, if we put these two fermions in Chern insulator states with the Chern number 1 for both of them, they become gapped out, they become massive, we can integrate them out, we get a topological transcendence theory. This corresponds to this fractional quantum Hall state, similar to this Charleston liquid I talked about earlier. Now, if we consider that one of the fermions has Chern number 1, the other one has Chern number 0, we can show that we get a transcendence theory that is trivial. So in fact, it has a unique ground state on all manifolds. And so this is the non-insulating state, which is a kind of trivial insulating state of bosons. And then finally, if we consider that these two fermions form Chern insulators of opposite Chern number, then if we integrate them out, there's no net transcendence term being generated. So the first leading order term is a Maxwell term, the free photon, which can be dualized into a free scalar theory. And the scalar field, this gapless scalar field, can be interpreted as the Goldstone mode of the superfluid. Okay, and that is how you find all three possible phases of these bosons. Okay, so we'd like to turn our attention a bit more closely towards this superfluid phase, okay, to see really in the details what is actually happening here, especially if we consider the compactness of the gauge field. Okay, so I said that we're going to assign these opposite Chern numbers to the fermions. In the continuum description, that means that we have 4 flavors of 2-component direct fermions. So we have this this sort of parton flavor label 1 and 2, and then on the lattice we have these 2 Vallée indices, K plus and K minus. So we have overall 4 flavors of these direct fermions, and to get this Chern number assignment, they have to have opposite masses in the continuum. So the masses are the same for the 2 Valleys, but they're opposite for the 2 flavors of partons, psi1 and psi2. And as I said earlier, they have opposite gauge charge under this emerging gauge field. Okay, so the continuum Lagrangian we can write down for the superfluid phases as follows. We have massive fermions coupled to a U1 gauge field with these particular assignments of quantum numbers. Okay, so if you look at this theory in the continuum, everything is fine. But if you remember that you're really on a lattice, then there are going to be non-perturbative effects to be accounted for, which are instantons. Okay, so one way to think about this is that the superfluid phase as a phase of bosons is not a fractionalized phase. Okay, so there should be no U1 gauge fields lying around in this phase, and so it has to be a confined phase in some way. Now we know that on the lattice QD3, because of the compactness of the gauge field, is prone to confinement because of the proliferation of instantons. Okay, so this is the seminal work of Polyakov, and we know that in the absence of any matter, then for infinitesimally weak gauge coupling, theory confines and becomes massive because these instantons proliferate. So what we'd like to understand is the effect of the fermionic matter on this instanton proliferation, because we have these fermions here lying around, and we'd like to know what happens in their presence. So the original political theory in the absence of fermions roughly goes as follows. So this is the kind of non-compact piece of the action that I wrote earlier. So this is the dualized form of the Maxwell action. But now we have these instantons that can be positions at which are basically Dirac monopoles in the Euclidean three-dimensional representation, and they're localized. They're point excitations that can occur at any point in space-time. They're created by this monopole operator. They have some Dirac topological charge QJ. They have a particular action for their creation. So we're on the lattice, so there's a finite action for the creation of these monopoles. And then we need to sum over all possible configurations of monopoles, their positions, and their topological charge. And so we get some kind of Coulomb gas of Dirac monopoles, of instantons, which if you resum this Coulomb gas action under some assumptions that, for example, only ±1 monopoles really contribute, then we get this Sine-Gordon theory that is gapped, and we get the usual confinement story. Now, in the presence of fermions, we need to add this extra piece, which will be the partition function, or the path integral of the fermions in the presence of a fixed monopole background, and then summed over all the monopoles. So whenever you have fermions in some topologically non-trivial background, you want to ask yourself whether there could be fermion zero modes to worry about. Okay, so a beautiful illustration of this is the classic work by Tahout, where he found that in the presence of the Yang-Mills instanton in 4 dimensions, the SU2 instanton, then massless Dirac fermions will have zero modes that are bound to the instanton. And if you resum this instanton gas in the presence of these zero modes, you will see that the actual U1 symmetry is broken explicitly, and that's its famous solution of the U1 problem in QC. Now, in 3 dimensions, which are dimension of interest, there was a study by Ian Affleck, Jeff Harvey, and Ed Witten in the early 80s, where they studied a model with a non-abelian H field, massless fermions, and also some Higgs field, where they showed that there's also a fermion zero mode that can occur, and that is protected by some index theorem called the Callis index theorem. And likewise, they show that this leads to an explicit breaking of a symmetry, a U1 symmetry, which here is again a fermion symmetry, but here is a fermion number symmetry as opposed to an axial symmetry. Now, if we look at massless QD3, so for abelian gauge fields, first of all, there's no obvious generalization of the Callis index theorem, which seems to rely heavily on the non-abelian gauge structure and the Higgs field. And also, Marston studied the zero mode problem and did not find any fermion zero mode solutions that are normalizable. So now we want to ask, in our massive QD3 setup, are there fermion zero modes, and will they affect the dynamics of instanton proliferation? So we did not find any index theorem, but we simply solved the problem explicitly, solved the Dirac equation in the Euclidean spacetime for zero mode, and we find indeed that there are fermion zero modes that are exponentially bound to the instanton or the anti-instanton, and the localization length is inversely proportional to the fermion mass, explaining in hindsight why Marston did not find any normalizable zero modes in the massless. So when you have these,
Joseph, 5 plus 5.
Okay, thank you, perfect. So why should we worry about these fermion zero modes? What is their effect? Okay, so in the Euclidean space-time, if you have a zero mode of the Dirac operator, this will kill the partition function. Okay, for the simple reason that if you compute this fermion path integral, you will get the determinant of this Dirac operator. And so if there's a zero eigenvalue, this will kill the partition function. Okay. And another way to see this is that if you're performing you decompose this Grassmann integration measure in terms of the eigenmodes of the Dirac operator, for the zero modes, they do not appear in the action because their contribution here will be 0. So you have these unpaired Grassmann integrations that give you 0 once again because of the rules for Grassmann integration. Okay, so physically what this is telling you is that the vacuum amplitude is 0, but there should be some symmetry breaking amplitude that are not 0, because if we have anomalous insertions with the right number of Fermion operators, then this will soak up the zero modes in the Grassmann integration. Okay, and so schematically, effectively, it's as if we had, as if these monopoles or these instantons would would act as a fermion creating vertex with, in this case, 4 fermions, and the propagators here essentially the role is played by fermion zero mode wave functions. Okay, so that is the famous de Hoogt vertex in the in QCD. Okay, but here we're considering it for this abelian U1 theory. And so to make a long story short, indeed, we can compute these insertions. The right number of insertions is in terms of these 4 fermion operators. And if we resum the instanton gas, we find this effective Lagrangian, where now we have this dual photon here. And so we only have the non-compact gauge fluctuations left, and the monopoles have been resummed or integrated out, if you will, this theory. Okay, and so we have this non-compact theory, but now we have this instanton-induced interaction vertex with a dual photon sigma, and then these fermionic operators. So the first effect is that as it should, these instantons break this sort of enlarged spurious symmetry of the original theory, which is the global symmetry of the bosons, which can be implemented as a global U1 charge for, let's say, one of the fermions, let's say psi 1. But there's also this U1 topological symmetry, which is a conservation of flux in an abelian gauge theory, which obtains for a non-compact theory. But this is a spurious theory, because a spurious symmetry, because we only have a single U1 global symmetry in the microscopic theory of bosons. And indeed, the instantons ensure that this enlarged symmetry is broken down explicitly to only the diagonal U1 subgroup, which is which shifts the dual photon in addition to rotating the phase of one of the fermions, and that is the physical boson number symmetry. Okay, so now we can try to understand where does a superfluid phase come from. So in fact, there's 2 possible superfluid phases that one can make manifest here. So if this interaction becomes relevant, then you expect that the dual photon will condense, and this is what happens in the Polyakov theory, the Polyakov story. Now, if the dual photon condenses, the first thing that can happen is that will happen is that this 4 fermion operator will also acquire an expectation value. So in terms of the original bosons, now this is some kind of exotic paired superfluid, because the boson is made of 2 fermionic partons. So if I have 4 fermionic partons, then I must have a paired condensate. So this is not this is not Cooper pairing. This is a pairing of bosons. And so if this is the case, then the U1 boson number symmetry is in fact only broken to a Z2 subgroup. So there's some kind of exotic superfluid. This residual Z2 symmetry can be further broken down through a subsequent Ising transition to an ordinary superfluid condensate, some kind of BC, where we have an expectation value of a single boson operator. Okay, so basic idea is that these fermion zero modes are really important to describe the correctly describe the possible occurrence of a superfluid in these parton theories. Okay, so this is all I wanted to talk about. So in the first part of the talk, I argued that there are new universality classes of critical phenomena that show up in these lattice QD3 and that have interesting condensed matter interpretations. And in the second part, taking into account the effect of instantons, I showed that QD3 with massive fermions has Euclidean fermion zero modes bound to the instantons that give rise to symmetry breaking effects that accompany confinement. So I'd like to thank you for your attention, and I'm happy to take any questions.
Thanks, Joseph. That's very excellent talk, and I'm not going to mention the embarrassing photograph Okay, so Simon's got a question first up. Simon?
Thanks, Joseph. It was in relation to the Callias theorem and how it might work in QED3. I believe that Polyakov's original demonstration of confinement in QED3 was actually motivated or kind of based on the idea that it was a low energy limit of precisely of the Georgi-Glashow model, with the instantons being tough Polyakov monopoles. So it seems quite natural that there would be a remnant of that theorem, assuming there's some scale breaking and that the fermions are gapped.
Yeah, that's right. So indeed, in this Georgi-Glashow model in 3 dimensions, that is indeed what you get. So the instantons there are, as you say, they're basically the Tohu Polyakov monopole, which is a soliton, now becomes an instanton in the Euclidean 3D theory. But the only thing, right? So I guess the connection, I think, is that in this Georgi-Glashow model, the fermions acquire mass. So we have these adjoint fermions that acquire mass through the condensation of a Higgs field. And then in that limit where the theory is abelian and fermions are massive, that resembles a lot the theory that we've studied here, this massive QD3 theory. But in terms of an index theorem, so our understanding was that if we look at the Callias's paper, really it involves the non-abelian nature of the gauge field, and also there's this winding at infinity of the Higgs field in the Tohu Polyakov solution that seems to play a crucial role in formulating a rigorous index theorem. So we couldn't see mathematically how to kind of make this story here rigorous. We have another way of understanding the topological nature, which is appealing to the Hamiltonian picture. So in the sort of SCFT, state operator correspondence picture, instead of looking at an instanton as a point defect in non-compact space-time, we could think of it as an operator insertion. And then we look at a sphere surrounding the monopole, and then we quantize fermions canonically on that sphere. And then there's a zero mode coming from the Atiyah-Singer index theorem for massless fermions. If the fermions are massive, then these zero modes are moved away from zero energy. And these kind of displaced zero modes in the Hamiltonian language seem to be in correspondence with our instanton Euclidean zero modes. So it's kind of a loose correspondence, but we don't know how to formulate a rigorous theorem. But maybe there's one. I'm not entirely sure.
So okay, Simon?
Yeah, I think so. I mean, from what I can remember of the Callias paper, it ultimately, you show there's a pair of modes and one of them becomes non-normalizable or something.
That's right. That's definitely the case as well here. So if you were to keep the sign of the mass the same and change the charge of the fermion, then you get e to the plus mr over r instead of e to the minus mr. So then it blows up. It's not normalizable. So these conditions kind of remains, which is why it seems that there should be an index theorem. It seems very topological in flavor, but I don't know how to make it rigorous. But yeah, I'd love to chat more about this. Maybe during the break.
Okay, Vladimir, have you got a question? You're muted. You're muted, Vladimir, sorry.
I think we can't hear you. I think your microphone is muted.
Microphone's off.
That should work better.
Yeah, go ahead, Vladimir. So we didn't hear your question, so if you could you tell us your question, please?
Yes. Could you name the papers where the short range Yukawa potential were direct verified?
So were the Yukawa potential what?
Once more, please.
So I couldn't quite hear. So you're asking about the Yukawa potential?
Yukawa potential, the short range Yukawa potential were direct verified.
So I guess you're probably talking about this earlier part of the talk, right, where we had these critical theory with the Yukawa coupling. Like this, you're talking about this Yukawa coupling?
No, I would like to hear the papers where was done experimental results on direct verified of short range Yukawa potential.
Well, for this problem, I'm not aware of a experimental realization of this.
Okay.
Yeah.
Okay.
It's numerical so far, yeah.
Thank you.
Okay, Valerie. So, Oscar, have you got a question?
Yes. Hi, Joe. Nice
Hi,
talk.
Oscar.
I have a question about actually this slide. Imagine I'm to the right of your QCP, so in the antiferromagnetic phase. My understanding is that you get ghost-on bosons from the phi field, but in addition to that, you get a massless gauge field, correct?
Yes. That's right. That's right.
So that's
this would be like,
that's
yeah,
an
go ahead.
That's an exotic magnet which has low-lying bosonic modes in addition to ghost-on modes. How are you thinking about that?
That's right. Yeah. So then if you just naively look at this theory, you would get this kind of AF star phase where it's a fractionalized antiferromagnet. But what happens is this is where the monopole operators become important. So here we're assuming that at the critical point, the monopoles are irrelevant because in the large NF limit, their scaling dimension is large, and so we can ignore them. In this antiferromagnetic phase here, the fermions are gapped, and so unless there's zero modes, the way that I talked about, but even if there are, the monopole will be relevant, and that will confine the gauge field. So this dual photon will be gapped out. So in a sense, it's not in this critical theory, but it would be there if you kind of add by hand the monopole operator that really should be there.
Okay, thank you.
Yep.
Okay, is there any other questions? Simon?
Yeah, I have a quick, it's not a follow-up, it's a different question. In the model that you have, the Lagrangian you originally wrote down, there were separate couplings for the electric field E squared and for B squared. Do you know if there's a limit where this model coincides with the QED3 model, which the lattice community have traditionally been concerned with over many years?
Yeah, so it's a good question. I'm not very well versed in the literature, but I would assume that obviously you want to preserve, Lorentz invariance as much as you are able.
Yeah.
So that somehow you want to make these couplings the same or something. So one thing I would say is, okay, so if you reintroduce various, the lattice constant, for example, in there, and I guess you also want the velocity of these fermions to be the same as the speed of light, right?
Yeah,
so also
sure.
you probably need to tune your hopping T and your J and K to some precise set of values, or at least two ratios need to be adjusted here.
I don't know if Rajamani is still on the call, but I mean, people have looked for a transition for a long time without really seeing any convincing evidence. It always looks like it's in I think what you're calling the U1D phase, the spin liquid phase.
Yeah, so here I guess you need to, right. So you would expect that, yeah. So I don't know if having Lorentz invariance is a prerequisite to see this critical point here. Right? They're not requiring it for sure.
Yeah, sure. Okay.
Yeah, maybe it's a better question for Fakir, because they are the ones who really wrote down and simulated this model. We just use it as motivation to study the critical properties, but yeah, it's a good question.
Rajaman is actually trying to say something, but he doesn't have a working microphone, so it's a little bit frustrating.
But maybe I can comment on that. So
go ahead.
Yeah, so the point is, like, what we are trying to do is a different limit, right? So what he's trying to say is he's trying to study a lattice model and asking for a lattice transition in the lattice model. So, I mean, I'm not sure, but looking at the J, it looks like what you call the beta equal to 0 limit is, I think, is going from an extremely strong coupling limit. And in that limit, the gauge fields are not smooth enough, right? So what we want to first do is, on the lattice, we want to take the smooth limit as a continuum limit, and then look at the IR limit. So that's not the limit in which this study is being done. So I'm not sure what is the correspondence. Whether this is the point that we would call as the infrared limit of a QED3 in a quantum field theory limit of saying.
Yeah, I guess when I said that J equals 0 tunes the strength of the quantum fluctuation, I mean, really at J equals 0, the gauge field, yeah, is crazy. It does everything at once. But it picks up this pi phase flux background. And then on top of it, and then the J makes the gauge field not classical, I guess.
And by pi flux, I think the corresponds to be something like a staggered fermion.
Yeah, sure. It would
and in this strong coupling limit, I'm not sure even a universality between fermions hold true, right? I mean, if you look at the staggered spectrum, the taste partners might not even be near each other.